Hello students, we are going to discuss water, solutions, solubility and also electrolysis. Now we know that water is the most important liquid present in the universe. We have seen water in various forms. Water comes to us in the form of rain. Water exists as clouds. Water comes out from the bore wells or wells, springs, lakes, rivers, seas, oceans. All these contain water. Now we require water. The life on earth depends on the presence of water. Now water as a liquid has got a high boiling point of 100 degrees Celsius, and the atmosphere on the earth at wherever places we are going to have water as a liquid. Some places water turns into ice. We also have water in the form of vapor, but we are dependent heavily on liquid water. And this water is a universal solvent. It can dissolve so many substances. It can dissolve glucose, it can dissolve sucrose, it can dissolve common salt. So like this, we have got water showing its properties as a solvent. And with water as a solvent, we get various aqueous solutions. And in these aqueous solutions, there is also electrolysis going on. For example, an aqueous solution of, let us say, copper sulfate can be electrolyzed, and we can get products of electrolysis based on the reactions. So that way what we find is that water is a universal solvent and helping us in making solutions and giving lots of important significance for our day-to-day behavior or day-to-day life. We can classify the sources of water as groundwater, that is under the ground, surface water above the ground, and then rainwater. Now groundwater is water coming out as springs. We can take this water out as well water or bore well water, which is under the ground. It contains lots of dissolved substances. Then surface water in the form of lakes, rivers, seas, oceans will also contain a lot of dissolved substances, usually salts, which is why we find that, for example, seawater is extremely salty. Then rainwater is due to condensation of water vapor from the clouds, and this is the purest form of water because we do not have much of impurities settling above. But as it falls, it carries so many substances, for example, sulfur dioxide, oxides of nitrogen, carbon dioxide, and then that rainwater turns acidic. So these are the three sources of water, and the water that we consume could be both hard and soft. For example, water that contains lots of salts of calcium and magnesium with bicarbonates, chlorides and sulfates will become a hard water, and water which is free from these or which has very less quantity of these becomes a soft water. So what is the difference between hard water and soft water? Hard water is that water which makes washing difficult. Means when we wash, we need to get complete cleaning of the area, and we require formation of froth or lather. So hard water is going to delay the lather formation. So what happens is, when we use hard water with soap, lather formation is delayed. We don't get the lather immediately, and therefore as long as the lather doesn't form, the washing doesn't happen, and therefore we require more and more of soap to form the lather. So in hard water, lather formation is delayed, washing is delayed, and soap is wasted. Thus hardness in water makes washing difficult. Difficult means hard, so that is how the word hard comes. So it is hard to wash in water. And this is because of what? Because of chlorides, sulfates, and then bicarbonates of calcium and magnesium. Usually any heavy metal ion, even lead or ferric heavy metal ion is going to do, but what we usually find is calcium and magnesium. Then what happens? It delays lather formation. Why does it delay lather formation? Because it forms a curdy white precipitate called scum with soap. Soap is actually a salt of fatty acid, a sodium salt of fatty acid. Now that sodium salt of fatty acid is going to be replaced by either calcium or magnesium. Means the sodium is going to be replaced by calcium or magnesium, and therefore the soluble sodium salt becomes insoluble calcium salt or insoluble magnesium salt. That insoluble magnesium salt is the scum or the curdy white precipitate. Now, when does lather form? When the precipitation has been complete. When does the precipitation get complete? When all the hard water cations are removed, that is calcium and magnesium are removed. So, if calcium and magnesium are more in water, then they consume more soap. They consume more soap to form the lather, and therefore soap consumption becomes faster in hard water. So imagine two people, one consuming hard water, one consuming soft water, taking identical soaps, and then we find one is going to buy the soap much faster than the other. So what does this mean? That there is a wastage of soap because of formation of hardness, because of presence of hardness in water. And therefore what we find is removing of hardness or making the water soft has lots of benefits. Next, hardness can be of two types, temporary and then permanent. A temporary hard water or temporary hardness is because of bicarbonates of calcium and magnesium. Now, this temporary hardness can be removed by simply boiling the water. When you boil the water, the bicarbonate is going to become insoluble carbonate. For example, calcium bicarbonate, if you write like this, CaHCO3 taken twice, upon heating is going to turn into insoluble calcium carbonate. So calcium bicarbonate, which was soluble in water and which was causing the hardness, has come out of water in the form of precipitate, and therefore this bicarbonate hardness is removed by simple heating. Similar thing will happen for magnesium. In the case of magnesium, magnesium carbonate could form, magnesium hydroxide also could form. Magnesium hydroxide is also an insoluble part, and therefore the bicarbonate is removed from the water. So bicarbonate hardness is actually a temporary hardness which can be removed by boiling, whereas permanent hardness requires certain special methods for removal. Why do we need to remove hardness? Water has calcium and magnesium which are good for our body, but this water being hard will have other problems, especially in boilers. In boilers, we have water turning into steam, and as the hard water is being boiled for days together, for months together, there is formation of scales on the inner surface. So the inner surface of the boiler will have scales. These scales are the precipitates of calcium and magnesium, and these scales function as insulators. They are insulators, and as you get a coating of insulator on the inside of the boiler, you need to heat more, because insulator does not conduct. They are thermal insulators, and therefore the conduction becomes less, and therefore you need to heat more, and therefore there is a wastage of fuel. Fuel gets wasted. It can also happen that the insulator, that is the scale, can have cracks. You can develop cracks because of wear and tear, and wherever the crack happens, that insulator is removed, and that part where the water is present is at a higher temperature than water elsewhere. That is, wherever the water is in touch with the insulator, it is at a lower temperature, and wherever the insulator portion has been removed because of the crack, there is a greater temperature. So when there is a greater temperature, this water is going to turn into steam, and steam puts pressure, and with this pressure the boiler may burst, and this entire thing will happen one fine day without giving any indication, which means that anything can happen to a boiler if not checked properly. And industrial boilers are not often checked because these are not small ones where the checking can happen. Just like in houses, if we have taken water in a vessel and we have repeatedly boiled this water, we have seen white scales developed on the inside, and this can happen because this we are seeing on a day-to-day basis. But in industries, what happens is the boilers are not checked on a day-to-day basis, and therefore it can happen that the insulator getting a crack, the water turning into steam, putting pressure, may burst the entire boiler. So that way what we find is, if the water is hard, there is definitely a danger of the boiler bursting. Therefore it is better that the hard water is made soft. So softening of water is a very important aspect when it comes to using of water in boilers. Now we are showing how hardness can be removed, and the first one is for only temporary hardness. How you are going to remove only temporary hardness, which we had already mentioned that it can be done by boiling. Now calcium bicarbonate and magnesium bicarbonate are present in temporary hard water, means hard water whose hardness can be removed easily by boiling. Now this calcium bicarbonate, when heated, turns into insoluble calcium carbonate. So that calcium carbonate is out of the water, and therefore the water is free from the calcium bicarbonate. Then similarly for magnesium bicarbonate, we could write a similar equation, but it has been found that magnesium carbonate is also insoluble, that there is also formation of magnesium hydroxide. We could also write a similar equation for magnesium, MgCO3 plus H2O plus CO2, but it is found that magnesium hydroxide is also insoluble and is therefore the product of the boiling of hard water containing magnesium bicarbonate. Now this is how calcium and magnesium salts of bicarbonates are removed by simple boiling, and therefore the hardness is called temporary, means we can simply remove by boiling the water. Now if it is temporary or permanent, suppose permanent is also there, then this boiling method cannot be used. Therefore we are to employ some special methods. For example, this is permutate process. Permutate is actually a synthetic zeolite. Zeolites are structures where lots of pores are there. Now zeolites are sodium aluminosilicates. So this Z we are keeping for aluminosilicate. So Z means zeolite. Zeolites are sodium aluminosilicates, and this permutate is a synthetic zeolite. Now this Na2Z, when treated with hard water, we know that hard water contains calcium salts or magnesium salts of chloride, sulfate and bicarbonate. We have taken just one example, that it is calcium chloride. So what happens here, the calcium sticks to the zeolite and sodium is out into the water. So hard water turns into soft water, means when hard water passes through the pores, percolates through the pores of zeolite, the Ca2 plus ions are stuck to the zeolite, and from the zeolite Na plus ions get into the water, and Na plus ions do not cause hardness, and therefore hard water turns into soft water. A similar thing we could also write for magnesium, whether it is sulfate or bicarbonate or chloride of calcium or magnesium, the zeolite is going to remove the hardness, and in this process Na plus ions are coming into the water and zeolite is taking up the Ca. So Ca comes on to the zeolite and zeolite loses the Na plus to the water. So water loses calcium or magnesium to the zeolite and zeolite loses sodium to the water. Thus hard water turns into soft water. So that is permutate process or zeolite process. Next is ion exchange process. Now, if you have seen this, it is only the cation that has been exchanged, means only the Ca2 plus has been exchanged, not the Cl minus. Whereas here in the ion exchange process, there are two resins. Resins are organic polymers, big molecules they are, and resins could be of two types, a cation exchange resin and an anion exchange resin. So this will call as CER, cation exchange resin, and this is anion exchange resin. Now when calcium 2 plus coming from hard water is passed through a cation exchange resin, the H plus ions get replaced by Ca2 plus ions, which means that the resin is going to gain Ca and going to lose H plus to the water. So water is losing the calcium 2 plus or magnesium 2 plus and gaining H plus. So the hard water cations are replaced by H plus. So H plus comes into the water and H plus doesn't give any hardness. Then in the anion exchange resin, we have got free OH minus. So the OH minus and SO4 minus are getting exchanged. So the resin gains SO4 minus or Cl minus or bicarbonate from the hard water and loses OH minus to the water. Thus OH minus is into the water, making it soft. At the end, what happens? This 2H plus and this 2OH minus will form 2H2O, which means that you're going to have demineralized water or deionized water. Means from water we have removed all the ions, and therefore in the ion exchange process using the resins, we are going to lose or we are going to make Ca2 plus or Mg2 plus or bicarbonate or sulfate or chloride all out of the water. So the water becomes deionized or demineralized. The permutate and the ion exchange resins that we have used in the treatment of hard water, that is removal of hardness, could be regenerated. What is regeneration? Means you are going to get back the permutate in the original form so that it can do the softening of water further. Now what happened to the permutate? We saw that if permutate was written as Na2Z and to this you have added calcium chloride coming from hard water, we are going to get calcium attached to the zeolite. It so happens that all the Na plus ions present in the zeolite are removed. So if no Na plus exists on the zeolite, then the hardness removal cannot happen. It is because of the exchange that is between Ca2 plus and Na plus that the permutate is able to remove the hardness. But if there is no Na plus on the zeolite or the permutate, it is no longer useful. Therefore, once it has turned into calcium zeolite, we need to add brine, that is an aqueous solution of sodium chloride, to regenerate the permutate. So again you are getting back Na2Z and the calcium 2 plus ions are removed and they turn into calcium chloride depending on the reaction. Now brine is used to regenerate the zeolite from a zeolite which has got exhausted. So this zeolite has got exhausted, and from the exhausted zeolite we are going to get back the zeolite in the useful form, that is Na2Z. Now how about ion exchange resins? We have got a cation exchange resin, we have got an anion exchange resin. Even here we know that the H plus which was existing in the resin got replaced by calcium, and if all the RCO are having only Ca and have lost all H plus, they are no longer useful, and therefore we need to regenerate using H2SO4, some acid which can remove the Ca or replace the Ca with H. So cation exchange resin is regenerated by using an acid, a strong acid such as H2SO4. Then for anion exchange resin, we need a strong base because you have to get back the OH minus. So a strong acid and a strong base are required to regenerate a cation exchange resin and an anion exchange resin respectively.